belt, so it's kind of. Okay, so this is 0, and this means that alright, so this equals 0, and that implies that Qi equals Q. And this is like that same, this is that same thing that I told you, like pretty much on every exam, your mass balance. I mean, I don't want to say always because you could throw a curveball, but usually you want to get something pretty simple out of the mass balance, which is just like in the equals out. So, all right, so then from there, you can do a component balance. And this is on the gas phase, so we're doing component balance on the gas phase. Okay. So we're going to do the change in the volume times the concentration, and that's going to be, we have our inlet, which is Q inlet, C inlet, right? So that's our in, and we subtract our out. So in minus out, and the only other term that can contribute to the gas phase is the rate at which it's being consumed, so the rate at which it's going into the liquid phase. Okay, does that make sense? All right. And then we go to ECG. So because the volume is considered constant, we can pull it out of the derivative, and we are going to get QI So we're going to end up with something like this. Because we pulled out the VG, right, and then we divided through. So this is QI times CI divided by VG. And then minus Q naught times CG divided by VG. But see, this is where you have to use this piece of information. So he only wanted it in terms of QI in his answer. So we had to substitute, whenever we saw Q naught, we substituted in QI. So essentially QI. And so that's these two terms, and then this is just the written, this is just RS written out from what he gave us over here. And then you have the VL, and see how everything's divided by VG. Okay. So this is the component balance on the gas phase. And now we just have to do a component balance on the liquid phase. Now, and as I said before, the reason we're doing this is because this dy dt is really dCg dt dCl dt. It's a, 2 by 1. So that's why we're doing, yes?
Can you distinguish your phase maybe just a little bit more?
I'm sorry, this is K.
Yeah.
Where's my H?
Well, just make your
we do the component balance on the liquid phase. So we got d over dt of L C L. Okay, so does anybody know, does anyone want to take a stab at this? And do we have any inlet or outlet in the liquid phase? No. Nope. We just have it coming in through the gas phase, and it's being transferred into the liquid phase. So the only term that's occurring in the liquid phase is the amount that's coming from gas to liquid by this rate step. Does that make sense? Kind of? Yes? Okay. So we just have, this will be RS times VL. Okay. So once again, we can, so there we, it's simply, so we can pull the VL out, right? So this, I'm going to rewrite that as VL dCl dt is equal to RS times VL. And then the VL's cancel, so we just have dCl dt is equal to the rate. And the rate is A L A C star minus C. Okay. So we have this equation and we have this equation. Okay, and that's essentially all we need. We can just write this out in this form. So write it explicitly. So this is dCg dt and dCl dt. Okay, and that's going to equal. So we have our 2 by 2 matrix, which he usually refers to as A. And we're going to have this multiplied by our y, which is CG, CL. And that's equal to it's something. I'm sorry. All right. Plus whatever's left over, we usually call that B. So this just becomes, you know, AY plus B. This is like what he's gone over, you know, in class, original linear system. Okay, so you can see that for the DCG, we have to look at all the terms that contain CG. So you have a negative CG times QI over VG, and that's the only term that contains CG. So this first term is just going to be negative QI over VG. Okay. And now we need the term, so it's this times this plus this times this. And that's just going to be K L L. And then this is just 0. Okay, does that make sense, how that came about? So this is just saying, to get dCg dt, right, I need to take CG times this plus CL times this. So this term comes from all the terms in this that have a CL in it. And the terms that had a CL in it were the CL times the KL So this is our system. This is what he asked us to find, and it works out. And if you want to, this might help to show, we have, so ultimately, if we multiply this out, VCG, VC, I'll just do it with this first term just to show you. It's this term times this term, so it's negative QI over VG and CG plus KLA VL over VG CL plus QI over VG CI minus KLA C star VL over VG. And if you do some comparison, this ends up equaling this, if you pull some terms out, you'll see that this term equals this term. If you do, just basic algebra, you'll get this. Does that make sense to everybody? This is actually probably more difficult. This is one of the more difficult mass balances that he's ever given, probably. Usually it's like a CSTR or a PFR, especially since at the point of this exam we haven't had, you guys haven't had mass transfer. We haven't had it, so it's kind of a confusing problem. But the gist of it is the same, where you're going to have to take a mass balance. Usually get the flows equal, take some component balances. The good thing with this problem too is he gave you the answer, so you can kind of work your way backwards. Okay. Any other questions before I erase this? Or you move on to the next one? Yes.
Why does RS multiply by VL? For the gas phase.
Right here?
Yeah.
Whenever you have a rate, so you're looking at the component wise. So I forget the exact reasoning, but when you do the unit conversions out, you're getting a rate per volume. So you want to multiply it through by volume to get the actual amount of the component that's coming out. Because you want the units to end up being the same.
Then why is it the liquid as opposed to the gas?
Because, sorry, give me a second. Oh, it's because the rate is dependent on the amount of liquid. So once it becomes saturated, like this rate is dependent on how much liquid is in here. The more liquid that accumulates, the lower the rate will go.
Yeah.
So it's dependent on this volume and not the volume of the gas.
Okay.
Does that make sense?
Yeah.
Okay. Any other questions? No? All right, so I'm going to move on to part B then. And this was, part A was worth 25 points. So on your exam, it's actually a pretty good portion. You can see it took us about half the class just to get this one done. So. So part B, a little bit easier. So he gives you parameter values. Okay. show that the ODE model can be rewritten as the following. Alright, so you should look at this and be like, alright, good, you gave me the answer already, so I really just have to, put in these coefficients and you'll get this answer. I'm not gonna show out the math unless somebody wants me to, but like negative QI, which is negative 2 over 1, which is negative 2. This is 0. KLA is 1. VL over VG is 4, so it's 4. Negative KLA is negative 1. Same with these coefficients. You just do some plugging in the values to get this. So this is of the form A, Y, plus B. And he says, show this model has a steady state solution. Now he always writes, in the actual exam he writes 3-1 transpose, but you guys know that goes to the end. He just writes that, so it doesn't take up as much space. Alright, so this is I'm pretty sure over all the exams I looked over, he always puts like a steady state question. So know how to, know what steady state means. It's usually a pretty, as he would say, trivial, answer. It's just the derivative when it's equal to 0. So if you set this equal to 0, you have AY plus B. And we usually put that over the Y to signify that this is at the steady state solution. And we can move things around, so we have AY equals negative B. And if we're trying to solve for Y, then we multiply through by the A negative 1 out in front. Go away, you get Y is equal to negative A negative 1. Now, one thing on the homework I noticed for the math lab, one mistake was a lot of people, I forget which column was it, maybe column 4. You guys mixed up the order of the matrix multiplication. In matrix, when you're multiplying matrices, the order matters. It's not commutative. So, like when you're doing this, you have to make sure that you multiply the A negative 1 out in front. This isn't the same as B times A negative 1. So, just make sure on an exam that you do that. So, we take the inverse of A, the negative out in front. I'm assuming you guys know how to do this. It's just 1 over AD minus BC. B, negative CA. So, negative 1, 4, 2, 1. And that gives us the answer 3. And as he gives us the answer, this is really just checking your work. This is the B from here. This was just the inverse. Does anybody need me to go through that in more detail? Good. All right. So that was worth 10 points. You can see it's worth a little bit less. Not as much computation. Do you guys mind if I erase this or no? So now he says define this y prime of t is equal to y t minus 1. And you want to show that the ODE model can be rewritten as dy. Alright, so at least when I took this course, this whole thing kind of confused me. What you're essentially doing is you're reforming the ODE problem so that you don't have this extra b term. And the way you do it, so you have this, so you can rewrite y of t is equal to y prime of t plus the steady state solution. And if you write this in terms of the derivatives, you get dy dt is equal to dy prime dt plus dy dt. But this is equal to 0 because steady state is a constant. So, and this is going to be equal to a times y prime plus y plus b. Okay? And then this is equal to a y prime plus a y bar plus b. That's just distributing the a. So we
That y in the parentheses is y bar,
this
the one next to it.
this is just y. Oh, I'm sorry. Sorry about that. Yes.
Why do you rewrite y of t as dy dt?
Why did I rewrite dy?
Why did you write y of t as dy dt? Is y of t a derivative?
No, I'm saying if you took the derivative of both
and
sides.
differentiate.
Sorry.
Okay.
So this is just, does this make sense how I got to this step? No? Yes? Okay. And then we just saw from the last part, when you have the steady state plus b, you're going to get this equal to 0. So this really just ends up equaling ay prime. So we have what we wanted, dy prime dt is ay prime. And the nice thing about when he asks, so he usually, not all the times, but when he asks a question like this, the good thing is that the A matrix is usually the same as the one from the previous part. So we had like A, y plus b, and here you have A, y prime. So even if you don't really know how to do this problem and get this map, the good thing is at least you still know what the matrix should be. It should just be your original A matrix. So if you're ever on an exam and struggling with that, just realize that the A didn't actually change. So from there, he asks, find the eigenvalues and eigenvectors of the A matrix. So our A matrix is -2, 4, 0, -1. And we need to find the eigenvalues. So it's given by the equation determinant of a minus lambda I equals 0, I think. So this is just lambda squared, plus 3 lambda plus 2. Equals 0. And you can factor this, so this will be lambda plus 2, lambda plus 1. And this just gives you that lambda is equal to negative 2 on lambda 1. Okay. Is everybody on the same page with that? It's really important you guys know how to do eigenvalues, so, and eigenvectors. So if this doesn't make sense, let me know. Yes?
It's going back to the part before it. I'm still a little confused what that's actually doing.
What this part is doing?
Yeah.
All this part was doing was, it's not really all that important to do the rest, to do the rest of the exam. This part was really just to get rid of this B. So
What
initially,
method is that though?
I'm sorry?
What method is that?
Has he gone over that in class, or?
I don't think we have.
Oh, really? Huh. This is like linearization, so, actually it's not linearization. What you're doing is you're, oh boy, it needs to talk. Okay.
I've never seen this before. I've seen it in terms of like just doing eigenvalues, but I'm confused.
He's never done this.
I've just never seen it first.
Okay, well, essentially all we did here was, because you have a steady state solution, you're essentially reforming your eigenvalue problem so that the derivative of the steady state solution is 0. So when you factor that in, you're essentially eliminating that portion of it, so that instead of having like, ay plus b equals whatever, you're just, it's like a deviation variable. You've never gone over deviation variables? No? ay equals. Okay. But does the map make sense or not really? Okay. Essentially, the only part of the only point of doing this this part of the problem is so that we get rid of the b and we can just solve like a linear system where we have, this, we have a 2 by 2 a x equals 1. Because if we have that b, then we can't really do the rest of the problems that he asks. It kind of makes it really tricky. And in the next part of the course, you'll learn how to linearize like a nonlinear system, and that kind of goes more hand in hand with this. So maybe he's just not covered that like quite yet with you guys. Does that make? It's not the best answer, I know, but it's kind of hard to explain like if you guys haven't gone over nonlinear systems and that. But this is just the gist to get you to the A. If he gives you something like this, I doubt he will then, because if you guys haven't gone over it, I don't imagine he tests you on it. But just realize, like I said, that the A matrix is the same. So I can, if you want to, I can ask him if he'll cover something like this in the exam. Let you guys know. So these are your eigenvalues. Does that make sense to everybody, right? And to get the eigenvectors, you just do, so you do negative 2 minus lambda 1, 4, 0, negative 1 minus lambda 1, times your x. This is your eigenvector. And you want it to equal 0. So you essentially plug in your lambda 1. So when you plug in lambda 1, this just becomes 0. I'm just going to erase that if you don't mind. And then when you do negative 1 plus 2, you just get 1. So you get that, and you need to multiply it by an x1 to get 0, 0. So a simple solution would just be 1, 0. Because you'll have 1 times 0 plus 4 times 0 is 0, and 0 times 1 plus 1 times 0 is 0. I'm sure he's gone over eigenvectors aren't unique. So like you could have really put any similarly for the other case, I'm not gonna go through it unless you guys want me to, but you get it. You get the second eigenvector to be 4, 1. So this is your first eigenvector, and that's your second eigenvector. You guys mind if I erase this? So that was worth 25 points, doing the stuff that apparently you guys have never done, and finding eigenvectors and eigenvalues. So that was a good portion of it. So the next question is, you're given the initial condition y is 0 is ci 0 transpose. And we want to show that the model has a solution for so you can kind of see this already taking form. Here's your eigenvalues, right? And here's your eigenvectors. He showed you this form before. Does this look familiar? No. Does this look familiar? Or?
Like from, yeah, from
Yeah.
here,
Yeah, those. Okay. You know, you just have y of t equals like c1, and then you use it as like eigenvector, or so he does like 1, and then e to the negative lambda 1t. Like that was from okay. So essentially, you just use the initial condition to solve for these constants, and this would be negative 1. So this is where we come back to our y of t, and the y of t is y prime of t plus y steady state. So this is that, I guess, that part, you know, this is where it comes back into play. We solve for the eigenvalues and eigenvectors for this matrix, and then we're just establishing the steady state solution, which is just constant, so it doesn't really, we don't have to worry about finding the eigenvectors and eigenvalues for that. So what we kind of did was we stepped back, used the deviation variable, and made it so that it had the form ay, you know, or ax equals y. Solved for the eigenvectors, eigenvalues, got those that we needed, and now we're saying, all right, well, now we need to kind of go back to our standard variable, so get out of deviation, and realize that our y of t is the deviation variable we just solved for plus the steady state. So we're going to have c1 times the first eigenvector times e to the negative 2t plus c2 4 1 e to the negative plus our steady state solution, which a while back was found to be 3, 1. And we apply our initial condition, so we do y of 0, right, is c1 times 1, 0 plus c2 times 4, 1 plus 3, 1. And he told us that the initial condition just ends up being that. Assuming you guys can work, can get from this step to this step. It's just two separate equations. So it's just 3 equals C1 plus 4C2 plus 3 and 0 equals